Okay, basketweave.cal, modeling the view through rollershades, a work in progress. I added that last bit to the title and it made me feel much better about the presentation. So this is definitely a feedback kind of presentation, and I would maybe just as we go, if there are questions or comments or suggestions from anyone, we can just do it as we go, because I'll be quick. Okay, so I don't really have the review slide, but there's a lot of different ways to model fabric shades. You can measure the BSDF. Counting showed great examples of that yesterday. There's some different trans hacks that you can do. There's, I guess, Jan Wienhold has a sort of direct normal fit, but they all kind of have some shortcomings, especially when it comes to evaluating the view through the shade. They might sort of get the energy right, but like we kind of want it to look, like if we can get it to look right, then it probably is right. And then we can say something about how well we can see things through it, and then potentially compare that to like the view through other shading technologies. And so the idea here is to take more of a geometric approach, right? Because there's sort of limits to the BSDF resolution, and you get kind of that noise, like it's not perfect. The direct normal thing doesn't work for the view rays because it's capturing a lot of that near scattering. And so the idea is to just kind of build this up. So I started with a basket weave because that seems to be a really common shade material. So here's a nice zoomed in picture of shade fabric. I think this is like labeled 5% openness. I'm calculating 6.6% here just by selecting some pixels. And yeah, so if we look at what a fabric shade is doing, it's can be broken into some components, right? There's some amount of light that goes directly through. There's some that gets reflected and maybe reflected twice or diffracted and then comes through. And then there's some that I think even this is probably mostly reflected around a lot, but that we can kind of consider as transmitted diffusely. And so probably the most important part is it getting directly transmitted or not, especially for view. And so a while ago, I'd done a version modifying grading.cal, but that assumes these square edges, right? And so the fall off will be like related to the tangent, and that actually doesn't really match very well with what you see from like the BSDFs, and it's just too quick. And so if we assume rounded edges, we get this 1 over cosine fall off, and that actually matches much more nicely with, like, for instance, Jan's direct normal fit, which also kind of matches with the measurements. So that was kind of the starting point. It was like, okay, well, we can calculate this based on the assume a rounded edge to the thread, which seems like a reasonable assumption, and then it's just kind of figuring out, well, what are these critical dimensions, and then we can kind of go from entirely a geometric approach to get the optical properties. Okay, so and so then this is where the mixed func material becomes the sort of perfect material for modeling what is a mixture of different things going on. So the first thing is locating and sizing the holes. And so now we're mixing between void, air, and then the thread, whatever we make the thread out of. And so just a 6-parameter mix func here. The U size and the V size, so horizontal and vertical, or X and Y if the shade is horizontal. Openness factor, the thread ratio. So if you had like a 3-and-2 basket weave or something else, you could kind of change that. And then also the depth. It does seem like the threads often get squished a little bit when they're made, and so they're not really round, and so it's not like a 2-to-1 based on the cutoff angle. And then with that, we can just kind of figure out the fill percentage at different angles and fill it in. And I ended up filling from both sides because you could fill from the top or the right, and then it looks right when you're looking in one direction, but then in another direction it looks wrong. And mostly this ends up not mattering because it's so small in the rendering. Okay. Then we already need to do a couple things just for the holes, right? So like one thing is the holes aren't all perfectly aligned, and if we leave them all perfectly aligned, it's going to cause some aliasing effects that wouldn't really be there when we're looking in reality because of the pixel sampling. So we can just randomly jitter those around. But then the other thing is this isn't really what it looks like when we're looking through a shade unless we're really, really close to the shade, right? And that at some point it goes from being a heterogeneous mixture to something more continuous. But if we just make it a continuous impression, which is what like the Roost fabric.cal or a BSDF is going to do, that doesn't look right either. It now suddenly looks too clear. But we can do both, and then we could use like another mix func and mix those together. So I just made a little like acuity model. And so this is a little weird because you now have to match the material to what your pixel, like what your renderings are going to be. Like, so basically the acuity of your picture would be the pixels per degree of your view opening angle. So if you're rendering like a 3000 pixel fisheye, right, you'd have 300 over 180 would be your acuity, and like a 20/20 vision would be 120 pixels per degree. And so then we can calculate with the ray distance material or the ray distance parameter how big the holes look, and then decide whether to render them as a blended material like this that's just sort of these are very dark, or to do them as holes. And then if we kind of center a mixing sort of S-shaped curve here on around that acuity limit as the kind of 50-50 point, then we can blend between looking at holes when we're really close to looking at something that's more continuous from far away, and that kind of matches our impression, right? And I think there's even studies that, right, like the view is perceived as better when you're farther away from the shade. And then you could also use this for doing, if you render at a high enough resolution, you can then replace the pixels with the observer's acuity, and so you could model 20/20 vision or 20/10 vision or whatever, and kind of see that difference. Other than, I guess you'd also need to blur whatever you're looking at for reduced vision, but you would do that kind of after the fact. So here's the difference there. So if we have no acuity adjustment as we move away, so this is just meters, so we're close and we see the holes, and then we move farther away and we kind of get all this like aliasing and noise. And this isn't what it looks like when you're looking at a shade fabric from 3 meters away, right? And you end up kind of missing a bunch of holes and getting these dark spots, whereas the blended model starts to give us a better impression of the shade, or at least that would be the idea. Okay, so that handles mixing the thread and the air, but then we still have to figure out what to do with the thread. And there's a lot of different things that are going on here. We have this anisotropic scattering along the thread direction, at least for a basket weave, right? Because we get all the horizontal threads are kind of working like a micro louver, and so they're creating this vertical band, and then the vertical threads are making these horizontal bands. And then there also seems to be this like intense area of like diffraction and sort of low angle reflection scattering, like maybe the one bounce stuff that is quite intense. And then there's also this like farther scattering that happens out here, this high angle reflection scattering that's hitting at these more acute angles. And then we also have to handle the sort of Fresnel style effects that the reflection, I think Alston showed, the BSDF, right? The reflection goes up at higher angles, which means your transmission is going down at higher angles. So you also have to account for that a little bit. So we can just use more mix funcs. So here's kind of just a comparison. We've got HDR on the top and then the material on the bottom. And I just kind of fit the rough. So these are using a trans 2 material, so I can get that anisotropic scattering. So the one for the vertical and one for the horizontal. And then I have to mix the sort of near scattering with the far scattering. So it's just using that normal roughness, which doesn't match the scattering properties, right? Because it's not just like a typical facet. Is that what it's, whatever the, like, that's a poor estimate for this more complex scattering. So you have to blend the two together and kind of figure that out. And I have no idea how we'd actually like tune these across manufacturers and thread types and whatnot, but it wasn't so hard to match at least this one case. So we mix between the thread orientations based on the aspect ratio of the hole, right? Because it's that inside of the hole that is where the scattering is coming from. So if you have a long edge, more like a long edge vertically, then you're going to get more scattering horizontally, and if you have a long edge vertically, you'll get more, or horizontally, you'll get more scattering vertically. And so for now, that's just a constant, but that could change with angle, although I think with the foreshortening, it always kind of ends up the same. And then we can mix between the sort of low angle scattering and the high angle scattering, depending on where we are. Now, this has another limitation because we're only ever looking at the, well, I'll show that in a couple slides. So we can kind of mix the near normal and far with this mix func, and then we can mix between the vertical and horizontal with this mix func. And so, yeah, you can see as the angle of incidence changes, that ratio between the near scattering and far scattering also shifts. But you can see these, like this artifact here. Like one observation I made is as soon as you hit that cutoff angle, you don't get any of the near scattering anymore, but you still get the far scattering. But the model right now is considering the X and Y independently. And so I just had to put in a condition, like if you aren't seeing anything through because of the other angle, then you just cut off. But there's this like band here because you hit that cutoff angle right here, and that shouldn't be there, but because we're looking from the view side, like this is considering a different angle of incidence than that is, even though the source is coming from one. And so I don't know if there's a way to know the source direction from within the cal file, but you really would need both to match it. But you only have the view direction, which is fine when you're on the specular direction because it's the same. But once you're in this scattering cloud, then thank you. Yeah, but it doesn't, I mean, I didn't because doesn't it not, I guess for this, it would be fine for the scattering, but it doesn't handle the diffuse stuff, but that would be, yeah, I can add another for sure. Yeah, I could loop back to that. Yeah, but yeah, no, that's, I sort of like had some limitations with the BRTD func on the view and then, yeah, didn't loop back to it. But yeah, so that's, I mean, this seems right. I was trying to set up a video of the fabric, but it's actually hard with just a sample because like this is pretty wide. Like this is 30 or 40 degrees that we're looking at. And so it's hard to photograph that with a sample because you have to be so close and then it looks different. You don't, anyways. So any ideas on how to validate any of this would be useful. So yeah, so here's the full material. It's quite a handful. So we've got the 4 different trans 2 specifications, and then we mix the vertical threads, mix the horizontal threads, mix the threads together, Then we make a non-transmissive version of the thread to mix the sort of opaque versus transparent at the high angles, so it reduces to 0, and then mix the whole thing together. There's like, you could also do a simplified version, because if you cut out this anisotropic scattering, then you really only need a trans material and a plastic material. Mix those together and mix with the shade. So of course, that's all kind of hard to set and make. So I made a Python script that kind of will minimize the difference of the diffuse-diffuse transmission. So basically, to specify, you need the geometric parameters of the shade, so cutoff angle and then dimensions of the threads and openness. So basically, openness, cutoff angle, and diffuse transmission. And then because the diffuse transmission is complex, I just run a minimization routine to solve for what the right trans materials are. And then you can tune the intensity of the scattering based on the material. And so then this will spit out that full material definition. And so then we can kind of go across different variations. So here's all the same Mermet fabrics in 3% and 5% in gray and charcoal. Let's see, I probably have a slide for that. And so I just ran all of these through that, through the script, the material builder, and estimated all the openness factors just from these images by measuring the width of like 10 or like of a 10 by 10 grid, and then measuring the threads and then subtracting that to get the whole size. If you pick pixels, it's really hard to like get it right and where that fall off is, but that's something that we're working on, because we're also trying to come up with a simple way to measure cutoff angle. But then for these, we have cutoff angle from goniophotometer measurements. So I cheated and used those. And then the diffuse transmittance. And so here's kind of how the variation works across the things, across the different parameters. And I think the thing that really jumped out at me here was that for the 3%, this fall off seems way too extreme. And actually, it doesn't match the measurements based on this, this aspect, right? So once we get to this really tight aspect, if I set the parameter based on the vertical cutoff, which is reasonable with the thread depth, then the horizontal cutoff becomes quite narrow. And that's because for this weave, you can see the warp, right? So these horizontal threads is quite tight and quite flat. And then the weft is quite wavy. Whereas for the 5%, it's much closer to square. And so you kind of get equal. And so the assumption about the cutoff angle, right? I kind of made this simplification at the beginning that there wasn't this weaving that if you take the middle, if you take the average, that's where that's going to happen. But then as the threads space apart, you now have this more open. And you can actually see that when you look at the fabrics, that the holes turn to triangles once you kind of get past that true cutoff angle. And so for now, with this model, you can kind of correct for that by just like baking the ratio. But I think there needs to be, I don't know if you can do that geometrically or not simply, but that was beyond my trig skills. And yeah, so then I also got some BSDF measurements from Tao Ning. I think the same ones that David was using. But I don't have good images of the fabrics yet, because I had to order the samples in the US. So I have them and I'll get them. But for now, I just have the stuff that's on MECO's website. And so from that, I could estimate the aspect ratio, because I can count the cells, and then the openness, but I can't get more precise measurements of what the true openness is. But here we fit the model at 3 different phi angles, looking at the direct hemispheric transmission. And one thing that's a little bit different here is the 45 actually cuts off the 45 degrees. So going diagonally across the hole, you'd expect that to have more direct transmission, but according to the BSDF, it actually has less. And so my model's going in the wrong direction, right? Because I've got this purple line over here, and I don't really know why that's happening until I take a good picture of the fabric. So for the 5%, this one's a little bit more interesting because it's actually has a rectangular hole, or I assume it has a rectangular hole. And so here you can see the phi 90 kind of matches up reasonably well with the with phi 90 on the BSDF, and then the phi 0 matches well there. But then again, the 45 goes, it's somewhere in between, and so it goes in the wrong direction relative to what the BSDF said. And then with the light fabric, the behavior changes quite a bit because we have so much diffuse transmission. And here there's actually not really that difference, which makes me think that it's something with the scattering rather than the direct visibility, that there's more of the near scattering at that diagonal angle. And so that, but I actually don't even know if this fabric has the same cross scattering or not. And then the 5% light. I think the other thing that I noticed is when I fit the materials here on the dark fabric, it basically would come out with like 0 for the diffuse transmittance, but you can see in the BSDF that we do have some diffuse transmittance, and so we're getting that imaging of the, or projection of the rear projection of the sun there, that doesn't show up in the shade, but it works reasonably well. So it's kind of a fun exploration with cal files. Another interesting thing is you would think, oh my God, you have 6 mixed funks, like this must be so slow. I think similar to what Alston talked about yesterday with the cal files, like it's still like 5 times faster than the BSDF. But these are like T6 BSDFs. But so it still was faster than the BSDF to run, and does have some advantages with the appearance and a lot less artifacts and stuff in the images, and potentially makes a way to more easily like estimate parameters, like just from samples, and that we don't need a goniophotometer to maybe do it. And it could have some advantages for looking at view and looking at glare, and all sort of in one material model that could have some advantages. Anyways, that's what I got. Thanks. That's where it's at. Yeah, so I did a study comparing the visibility through roller shades and Venetian blinds and electrochromic glazing. And so that's when I initially developed this model and didn't consider the direct sun part at all. I mean, like the sun, the diffuse transmission on the sun, but with the sun out of the field of view. And then I used like some visual difference prediction to kind of estimate how much of the view is preserved through these different technologies to try and find a way of comparing across. But then when I was working on this for this, I kind of got into the idea of also modeling the direct sun and the scattering, which is the more, so yeah, but yeah, the initial impetus was for the view through it. So the yarn does have some trans component that you have to kind of solve for, because it also has this transmission fall off. And so the trans material, so like here in the simplified model, like oh wait, maybe not that one. Um, Result came out. Yeah, but so it does have a diffuse transmitting component as part of like to handle the very high scattering. And so that adjusts between, and so that's why you need the diffuse transmittance to set it, and that's what makes the dark fabric and the light fabric different. Yeah, exactly. Yeah, or but not using the manufacturer's transmittance because it's just some measure. Yeah. So what you need openness, diffuse transmittance, and cutoff angle are the yeah, and sometimes it's correct and sometimes it's not. Yeah. Um, so yeah, so most of these I got from publication. Like I think I integrated the BSDFs for the or maybe out of tables in the paper, and then for the other ones, Caroline and Carmen had a paper where these other materials were from, and so I used their measured values. Um, yeah, I think fitting to BSDF, if you had it, would be pretty easy because I think then you can even get the scattering. For the simplified measurements, the big thing that's missing is a simplified way to measure cutoff angle, which I know Jan is we're talking about working on. That's why we got this camera that can take these very nice images, but figuring out how to accurately capture that cutoff angle is tricky. But then once I think it is cutoff angle, diffuse transmittance, and openness. And then maybe one more for the scattering effects, which might be fit from a single scattering image like this, pulling a couple parameters and then going. But yeah, the idea would be find a way to do it without a goniophotometer. Yeah, I think that, I mean, what's interesting is I think it's so stippled, the specularity is quite like complicated. I think the cutoff angle is pretty, yeah. Because you need the depth, I guess. Yeah, yeah, yeah. Mhm. So from a perpendicular picture, derive the cutoff angle. That would be the ideal way to do it. Yeah. Right. Um, well, that's basically what I did here, but I didn't use Gen BSDF. I just used like R-trace and then ran through angles. But Yeah, I still haven't figured out the BSDF view, like now that Andy's tool, and I know like you have the tool, but it doesn't work for tensor trees. And oh, it does work for tensor trees now? The online one or or oh, you do have one. Okay. Yeah, so yeah, what's like the best way to sort of compare to BSDFs? The yeah, because it seemed like doing that directly from the cal file would be better than introducing the BSDF sampling, unless you're comparing the whole like three-dimensional BSDF. But I just don't know a good way to like reduce that data and like compare it all. And just seem yeah, I haven't. It seemed like a lot of work. Yeah, but it's just you just suddenly have so much data, and it's like, well, what would even be good? But yeah, I think it's that near specular part that whatever's going on at 45 degrees is the major limitation. Thank you.